Good morning, everyone, and welcome to this presentation. I'm delighted that so many people could make this. I know it's been a long week, but there's been an incredible energy over the last couple of days that I've never felt since I've been coming here, I don't think. And I'm sure it runs from top to bottom. I mean, from northern Labrador to southern Newfoundland, from east to west. But my home is in Bay Verte, and I've had a great career in mining so far, and 5 years ago, I got into technology development, but most of my life has been in production. And so I've been on the side of the desk where people were trying to sell me something. And now I've gone around to the other side of the desk trying to sell something. And I'm hoping to learn from the great salespeople that impress me to share our technology. So we've got a Novamera set up, incorporated about 5 years ago to develop technology for small footprint mining, and we call it surgical mining. And if anybody has had the benefit or had to have any kind of laparoscopic surgery, you know that your healing time is much less, and there's no scars. And that's what we hope to do for mining. We started out with a great relationship with the university and the college to help us with the science, and we've migrated now to a team of 15 people that include software and hardware and engineers and data scientists. So we're pretty pleased. And it's interesting that I'm in this group here because apart from knowing almost every single presenter that presented here today, I've worked with many of them very closely in developing many of the deposits that have been discussed here, including Hope Brook and Hammerdown and Pine Cove. And I've got to know some great people. And a lot of these discoveries go back many years, and we're waiting for a favorable gold price to go in production. And some of these deposits take a long time to get into production. And there are many reasons for that. Open pit in a geology that we're working with quite often in a very narrow vein. Examples like Romeo and Juliet or Deer Cove on the Bay Verte Peninsula, but in some other deposits across the island, the geometry is not favorable for conventional mining techniques. In the sense of open pit, there's a big excavation of waste rock that makes it uneconomic. And some of these, even though they're high grades, the amount of capital that it got to go in for a conventional underground make them uneconomic. And this image to the right here just compares the two. In the background is the Pine Cove pit, which was a 12-year mine, and it's probably, I think, as far as I know, the longest continually operating gold mine in Atlantic Canada. But its geometry was favorable, and it went in production. Right to the actually northwest of that was a discovery that was made at the same time that never went into production, and it really comes down to geometry. The grade was about 4 times higher, but the geometry prohibited from going into production. So we always ask ourselves, what if we can mine differently and develop a technique that would leave a very tiny footprint? It would enable faster to ore, and we'd have minimum waste to deal with, and we could generate some highly profitable returns. And that image is actually the proof of concept site that we worked on about 3 years ago. And again, there's a quartz vein here that extends about nearly a kilometer, 300 meters, I'm sorry, and very well defined, exposed in many places along there. And this could be the technique to do that, and essentially to mine down the vein from surface. So in the proof of concept, when we done this, we actually brought in containerized equipment, which is a drill that's used in marine construction primarily. And from the time the drill arrived on site till we were operational was about 48 hours, and we were in ore. We were actually drilling in ore as this deposit was exposed on surface. There's a lot of benefits to surgical mining as we are starting to evaluate. We never set out to develop a means to address the environmental challenges. we set out to develop a way to get ore to our mill. One of the things we quickly realized since then is that the opportunities around faster path to production, lower capex, and a small footprint are highly advantageous. And for that reason, I know we've got a lot of Australians here that have come to Newfoundland to work with us as we develop, but we've actually reached out and have people in Australia that are interested in working with our technology. So it's a small world, and we're pretty pleased to be a part of it. Just to bring in a little bit about what we do in more detail, it's AI-powered surgical mining. When we drill down these long holes, we don't have the benefit of being able to send a geologist down at the bit to determine if we should be turning left or right. We had to do that ahead of time, and we use a scanning device called an in-bit tool that we lower down in conjunction with the production through an NQ size borehole. And essentially we scan around the perimeter of the hole, reaching a distance of about 3 to 5 meters. So we have basically a virtual diamond drill hole that's upwards of 8 to 10 meters in diameter, and we can certainly project that. The entire system of surgical mining is basically a closed loop. We're working with a diamond drill that works ahead of the production unit to map the vein, and behind that we have the production drill, which essentially is a pile top drill that will drill down a steerable hole down the vein from 1 to 3 meters in diameter. And then as an essential part of the process, we actually got to follow that with a backfilling process where we put in the material that we've taken out, minus the ore, and to reclaim in a progressive manner the entire work site. This is a video here that basically animates the various phases of what we do. This is Beaver Peninsula. This is the Pine Cove mine in the foreground, and this is out in the vicinity of the Romeo and Juliet vein. And that white line to the north there is the periodic exposure of the quartz vein that occurs along the 300-meter strike. So there's a small, just a conventional diamond drill. We're using NQ, drilled down approximately parallel to the dip of the structure, and map the entire unit out. Standard coring, we've done that in multiple projects now in Newfoundland. We worked in Ontario past year, and currently we have technicians and drilling in Brazil doing the same thing. So it's very accurate, centimeter accuracy of vein mapping, and we're able to monitor not only the lithology, but we can pick up structure as well, and putting that together in a very high quality resolution. And we're using at this level conventional mining software to map to present the vein and the geometry of the area we're working in. So this is the first step in how this system works, to get very accurate geometry, and then subsequent to that, then we would come behind in with the large production drill and excavate the vein. That's a steerable system. The drill itself is an off-the-shelf unit. The bottom blue colored units are stuff that we fabricate, and that's a steerable part of our technology. But people in oil and gas, they're using this technology all the time to steer production wells, and we use the same thing here. It's a series of push pads, and it keeps us on track on the desired trajectory. It's a reverse circulation, so we keep the hole full of water, which helps stabilizes the excavation, but it's a very cheap way to get the cuttings coming back to surface. So the cuttings come back about 10 millimeters, so they're ready to go to a processing plant, not needing any crushing. And it's a pretty self-contained, very small footprint, and quite mobile. The big thing we've introduced now is the whole thing around surgical mine planning. This is a vertical mine. This is not like a conventional mine where you develop levels. There's all kinds of software that works on that, like the Deswick and so on. We had to develop a unique software to actually calculate the values on downhole of each single production hole. And we run multiple scenarios simultaneously to get the optimum dip and optimum diameter and optimum trajectory in azimuth to maximize the hole. And so each of these holes, which are represented in this image here by cylindrical shape, would have an X, Y, Z and a dip and an azimuth and total tons excavated along with grade. We do, incredible detail, conventional drilling. Typically, you drill down, you get what you want to get is the hanging wall position, the footwall position, and the grade, and that's it. Whether it's a 400-meter hole or not, all you're looking for really is those 3 bits of information: the start, and the end, and the grade. In this technique here, we get an estimated 4,900% more data per meter of drilling, simply because our radio scan is returning such a high definition and so accurate. And other people talked about, presenters talking about having to drill, Dave mentioned that the need to drill at 9 degrees from what was previously done. This image on the left here is actually a drill site in the Pine Cove area, where there were 4 holes that were drilled almost at 9 degrees to each other to help understand what the ore body is doing. And it could be very complex. And now with our technology, we can actually drill 1 hole, but we get the virtual benefit of an 8-meter diameter borehole, which gives you a lot of data. This middle image is deployment in central Newfoundland at a project with Sokoman, and hopefully going back at both of these sites in Newfoundland this year with Sokoman and the Great Atlantic to continue this process. Some of the ore body knowledge and the impact on extraction is just getting such a high resolution. Many of our projects and mining projects, you got 25-meter spaced drilling. And in between that, you're often scratching your head. And I know this from experience. It can be very challenging. Our idea is to firm up on a very tight spacing. So these images here would show you that how much could be gained with additional knowledge. Now, this was actually taken from conventional delineation, infill of a client's data. And with better knowledge, we could have actually forecasted a much higher vein recovery. So this is the step 3, the extraction. Again, there's a couple of images, but it uses a process of reverse circulation, but it's guided by the mapping and the software for trajectory planning. These are some of the images when the material comes up from surface. It's a very simple solid solution separation. Everything you bring out is typically heavier than water, so it'll sink right to the bottom. And because we reuse the water, the fact that it's still dirty going back in the hole doesn't cause any loss at all. And in this case here, we just use an excavator and pull the cuttings out. So what's coming out here, in this case here, is worth about $500 a ton at the grade that we were mining here. And this sample bag is the first surgical mining cuttings in the world. Although this technology is used in construction, it's never been used in a mining application. So it's a new application for it. So a lot of benefits from a financial perspective. The ability to improve IRR is significantly better than conventional, and the whole process of permitting. With surgical mining, typically we would not trigger the Metal Mines Effluent Regulations, which are often triggered by the volume of discharge. In 50 cubic meters a day, then you trigger the Metal Mines Effluent Regulations. We all talk about Newfoundland being a great jurisdiction for mining, but Newfoundland also has a Small Mining Act, which if the project qualifies, exempts it from many of the requirements of the Mining Act. So, which allows extraction up to 100,000 tons a year, and it hasn't been used a lot, but it is an opportunity here. Again, great value in terms of the everybody's concerned about when you make an investment, about getting your return back. The big thing about this is that the capital is portable. So it's not like when you develop a conventional mine where you sink a shaft, do your lateral development, because when that project is over, that capital stays in the ground at that location. With the technology that Novamera has developed, you move the capital to the next project. And the equipment that we use for our proof of concept actually came from, was brought in from the Netherlands. So it's pretty mobile, it's containerized, and it enables us and clients to get to a much faster production to use the equipment that we have. So, apart from the production, which was our initial goal here, to use these tools in production, it also can add a great deal of ore body knowledge. And we deployed the equipment now, as I mentioned, we're in Brazil, and we were in Ontario this summer, and these were specific for ore body knowledge. And again, we got the virtual benefit of a much larger diamond drill hole. We offer many services to the industry, and I was fortunate that I could participate at this event after so many other juniors have presented here, because it's fitting that although I never paid to get the ability to sleep in, I took advantage of it. So we're pretty pleased, and this is a made in Newfoundland solution. We've had a lot of benefit from and support from the academic, Memorial, and the College North Atlantic, and we have an end-to-end solution here, from doing the analysis to surgical mining. We got great partners in all aspects from engineering, but we also have finance partners as well who are interested in the opportunity that surgical mining will provide. I got a lot of people to thank, but I'd especially like to thank the people in the audience here, and I hope you've had a great event. And if you're a first-time visitor to Newfoundland, I hope it's been great, and I'm looking forward to seeing everybody again. So thank you.
Here, I'll go.